Okay, let's start. Okay, welcome everyone to the DDPS seminar. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk unless you have questions. If you have questions, you are welcome to unmute and ask. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed. So please watch out. And finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now let me introduce our speaker today. It is an honor to host Kaushik Bhattacharya, who is Howell Tyson Senior Professor of Mechanical and Professor of Material Science, as well as the Vice Provost at the Caltech. He received his bachelor's degree from the Indian Institute of the Technology, Madras, India in 1986. His PhD from the University of Minnesota in 1991, and his postdoctoral training at the Courant Institute for Mathematical Sciences during 1991 to 1993. He joined Caltech in 1993. His research concerns the mechanical behavior of materials and specifically uses theory to guide the development of new materials. He has received the von Karman Medal of the Society of Industrial and Applied Mathematics in 2020, Distinguished Alumni Award of the Indian Institute of Technology in 2019, the Outstanding Achievement Award of the University of Minnesota in 2018, the Warner Coiter Medal of the American Society of Mechanical Engineering in 2015, and the Graduate Student Council Teaching and the Mentoring Award at Caltech in 2013. Today, Kaushik will give a talk with the title of Multiscale Modeling and Neural Operators. Please expect a wonderful talk and enjoy it. Now, without further ado, let me pass the baton to Kaushik by asking our usual question. That is, what is your favorite things to do other than research?
Well, I'm looking at it. I'm actually staring out of my window into the mountains behind. So going for walks in these mountains is probably what I do.
Very nice, very nice. Getting some fresh air, right?
Some
Yep.
fresh air, yeah.
Okay, the stage is yours.
Thank you. Thank you, Young-Soo. It's a great pleasure to be here, and even though it's virtual, and share with you some of the kind of fun we've been having over the last 2 or 3 years. All of this is largely a collaboration with Andrew Stewart, who's an applied mathematician at Caltech, and Anima Anand Kumar, who is a computer science also at Caltech, along with a large group of really wonderful and really sharp students and postdocs. The work I'll talk today about is largely the work of Nikola Kovacsky, who's a graduate student in applied math with Andrew Stewart, Brigitte Liu, who is a postdoctoral scholar with me and is now on the faculty at Cambridge University, Margaret Trotner, who is a graduate student also with Andrew, Zhongyi Li, who is a graduate student with Anima, Kamyar Aziza Denashali, who used to be a postdoc with Anima and now is on the faculty at Purdue. I'll also mention works by Hao Zhu, who's a graduate student with me, Yingxi Te, who used to be a graduate student with me, but now at Livermore, and Akila Rajan. So let me kind of tell you the kinds of problems I'm interested in. One is trying to understand the plasticity, and especially in the context of dynamics, the plasticity of low symmetry materials like magnesium. Magnesium is the lightest metal and has very high strength to weight ratio, but it's also very It's not ductile, so it has very limited ductility. So what we'd like to understand, and the reason for it is that there's very complex individual slip systems because it's a low symmetric crystal. And what we'd like to understand is how do these slip systems affect the macroscopic behavior, for example, when I'm doing some kind of dynamic impact calculation, as it gets filtered through the polycrystalline microstructure. Second line of work, quite distinct, but very similar problems come in. I'm interested in active materials, and in particular, a class of materials called liquid crystal elastomers. So these are rubber-like solids, but they have pneumatic messages embedded in their main or as side chains. And because of this interaction between kind of the entropic rubber elasticity and the physics of liquid crystals, phase transitions in liquid crystals, they can undergo large spontaneous deformations and also form very strange domains and have very unusual macroscopic properties. Here I'm showing something which happens if I take a rod and I twist it, it ends up buckling in this particular way. So, and we're trying to understand the macroscopic properties starting from this kind of very small scale physics, which we understand well. Here's another recent work concerning DFT. Over the many years, Michael Ortiz and myself have been trying to develop a method of trying to do DFT studies of defects like dislocations where the far field matters. So we would like to do multi-million atom calculations of DFT so that you can fully resolve the core. And one of the ideas is really to do some subgrid sampling of the electronic fields. And that means that we end up doing a lot of unit cell calculations and and that provides a kind of predictor or a preconditioner for this method. So these are the kinds of problems that I'm interested in. And so let me focus on the one on the left. If I were to do a calculation like this classically, I know the kind of balance laws of continuum mechanics, but then I have to have a closure relation which tells me the relationship between the deformation history at a point, which I'll call f of time, and the state of stress. And classically, we have done this by empirical constitutive laws, and they have been very helpful and useful. They're still very useful, but we'd like to understand more, especially if you want to do the inverse problem of trying to design the material. And multiscale modeling provides a framework. And the recipe of multiscale modeling is, you know, the macroscopic deformation gradient and its history. You use that in a smaller scale calculation, often with periodic boundary conditions. So at the grain scale, you use this to provide you the boundary conditions, and then you solve the smaller scale physics. From there, you extract the stress history and use that in the larger scale problem. So the small scale problem basically provides you with the small scale problem provides you with the closure relation necessary for doing the large scale calculations. Okay, and of course, this is I'm describing it only at two scales. This framework of multiscale modeling works at multiple scales. You can think of multiple scales going all the way from electrons to your macroscopic simulation. And the kind of intellectual idea behind multiscale modeling is at any time you only have two scales really communicating. It's a pairwise communication where the larger scale regulates the lower scale by providing a boundary condition, and then you filter the results of the lower scale to the upper scale, right? And so you can use this cascade. And so coming back to this, if I want to try and really do this, what I have to do is I have to do a large number of repeated solutions of the fine scale problem. If I want to kind of just take this philosophy and want to implement it without thinking, what is called FE square times, what I have to do is at each grid point of my macroscopic problem, I have to start a microscopic problem, solve it, and put it back, right? So you really need a lot of repeated solutions. So of course, it's extremely computationally expensive. Second, you have a problem of generating representative microstructures because you really are not tracking all the details of the microstructure of the small scale problem. So based on some average, you have to somehow generate the small scale problem. And ultimately, you're doing these very large calculations and you're using only a very small portion of the information, right? Because you're filtering all this away. So you're doing these massive calculations and then you're using it. So this is what motivates our work. So if I think of this as a map from the deformation history to the stress history, can I learn the solution operator of the lower scale problem using the data generated by repeated solutions? So I solve this problem repeatedly, that provides my data. Can I learn this map then? And in some ways, can I also try to learn some hidden physics or closure relationship from this data that I get by repeated solutions? So those are the problems which motivate me today. And that's kind of what I've been trying to understand. And that's what I'll talk to you about today. I wanted to emphasize that our goal here is really learning the solution operator. There is a large body of work that is coming where you postulate what happens here. And of course, you don't know the parameterization. So you postulate a parameterized model and use machine learning for learning the parameters, right? That's not what I'm doing. I really want to learn the solution operator. So that's something which I wanted to emphasize here. Okay, so this is the problem. So I am given an input-output map. So I'm given the strain history, initial microstructure, and I want to find out the stress history and the first thing you realize is that this is, in this case, it's a strain history. So it's a function of time. So that's a function. It's not discrete data. So it's infinite dimensional. So the maps we are interested in learning is from one function space to another. So we're really trying to learn a nonlinear operator, right? So these are function spaces. So these are infinite dimensional. And I think that's important. So the data we have is we don't know this map, but what we are trying to do is we know realizations of this map. So in other words, we know pairs of input functions f and output functions s, such that s is a function, is this map. And f is drawn from some distribution which you may or may not know, and that's something which I'll talk a little bit about, right? So that's the data I have. And what I'm trying to do is to find an operator, psi, which is parameterized by some parameters theta, such that there is some value of this parameter theta star at which this operator will approximate this operator, right? So the problem of training is the following. So from this data, I have to kind of postulate some architecture here and use this data to find the particular parameterization. That's the kind of math problem I want to do. So it's completely supervised learning with the given data coming from some map. So I'll show you some examples of this. I'll talk a lot about what I'll call the PCA net, and I'll mention some really recent work, ongoing work, which we're very excited about RNO net. And I'll make some comments about other methods of doing this. So what are the challenges in doing this? One is, of course, what is the architecture that you should choose for doing this? Second, your data comes from either numerical simulations or some experiment, and it's discrete. So you don't really know the full function. You only often know the function sampled on some finite grid. So you only know it projected on some finite dimensional grid. But you might do a simulation. I might do a simulation. It might be in different resolutions. So we want the operator to really learn the functional relationship. So we want it to be independent of this kind of resolution. And when I'm trying to use it, I might want to use the resolution relevant for my macroscopic calculation. So it's also very important, therefore, that this operator that I find really represent the operator and therefore be independent of the resolution of the data that I have. And the third kind of challenge is really trying to identify the distribution from which the data is drawn. So that's an important thing. Okay. So let me begin. I'll first begin by introducing PCA-net, the one in which we have explored the most, and then I will generalize down the road to a broader architecture, which has a similar structure. So again, we are trying to learn the map from one function space to another. So here's the architecture we're going to use. And this is just what we postulate. And on the upper right, I have noted the name of the student of the postdoc who did bulk of the work. And in this case, this is really the contribution of Nick Kovacsky. So you have a function space. So you have a function space F. So what we're going to do is to do a projection of it to a finite dimensional space. And then I introduce a lifting back from this finite dimensional space to the original function space. So you can think of this as the PCA, in which case, depending on the data you have, you choose a basis set and represent your data in that basis set. And then, of course, that provides you also a lifting operator. You could also use a kind of a deep neural net in terms of an autoencoder, for example, where this is the identity map and this is the small dimensional layer in between. Right? So that's what we do on the input space. We do the same on the output space. Again, we project and lift. Now I have a finite dimensional representation of the input and output space, so I can use my favorite deep neural network or graph network or whatever architecture I want to use, right? So I'm going to go. Right. Okay. And then so the overall neural operator then is the projection, the finite dimensional network, and then the lifting. So I can write it in some compact way in this way. Okay. Very good. So that's what we're going to do. And for this, we can prove the following result. So before I show you some numerics, I'll actually tell you the kind of results that we can prove. So we're going to assume for this theorem that these are Hilbert spaces. We can now actually extend this result to Banach spaces, but we're going to assume that the input and the output spaces have a Hilbert space structure. We're going to assume that the map that we are trying to approximate is Lipschitz. We can again relax this. So these are the projections and the lifting are done through PCA. Mu is a probability measure on F, which we know. Then we say that given any parameter, I can find dimensions for my reduced space and a set of parameters for my neural network such that the expected error over all of the space F, expected over all choices of data, is going to be bounded. So that's kind of an approximation theorem you can prove. And I'll make a couple of comments. Notice that we assume that we know the probability measure from which our data is sampled. In actual problems, that may or may not be true. We need sufficient data for training because this is basically saying that the only way we can bound the error is by taking some expectation over all possible data. Maybe I should have also mentioned here that what you can really do theoretically, like in all these kinds of approximation theorems, is really bound the expected error. You can't really bound the absolute error or the maximum error. You can only bound some expected error. And you need some regularity, in this case, Lipschitz, right? So let me show you a very simple example. I have this partial differential equation. So the kind of a simple, you can call it elliptic problem. A is a positive number. And we are looking for the map from this coefficient A of x to the solution U of x, right? So that's the map we are looking for. A might be in some H minus 1, U might be in some L2. So it doesn't have the Hilbert space structure, but okay. And we're going to sample this from some distribution. So this is A of x. We solve this problem, generate numerical solutions on some grid, 421 by 421. We downsample it to some dimension, and then use that to fit our neural operator using a PCA dimension 70 and some things like this. Okay. So here's the A of x. Here's the ground truth of some particular U of x. So this is my data. And then in this particular case, this would be what the trained operator would be, and that's the error. So this is a particular realization, but more generally, let's look at it out here. Okay. So what I have is the relative test error average over, so I train it over some training data, and this is really some separate test data, and this is the error in the test data, expected error. So though I do my simulations of 421, the data I use is downsampled from there, and I use it for training at about at 64. So I downsample it at 64. And then I'm going to test it at 64, at 100, and all these other resolutions, all downsampled from the original data. And what you see is that our architecture, let's look at the blue one, where the lower dimensional was 70. You see that basically this gives you a resolution independent error. The error is about 5%, and it's resolution independent. Now,
Kaushik, after downsample and when you compute the relative error on the higher resolutions, there's just some missing points. How do you compute the relative error?
Okay, so the original data I generate is at a very high resolution, 428. That's 421 squared. That's where I did my numerical simulation.
Right.
Right? Very good. Then what I do is I downsample that to 64, right? 421 squared to 64.
Yeah.
I train my neural operator with that.
Right.
And then I test it with other test data at 64, but other test data at 200, 300, and so on and so forth. So what this is showing you is though I learned the operator with 64 dimensional data, the operator actually learned the solution operator, which is resolution independent. And so if you have data which is, if you test it against data which is at a high resolution, it still does it. And the reason for this, and where this is really where the PCA part helps. So when I'm not training the architecture based on the data that 64 I have, but I did a PCA which tells me something about the distribution of the data, and I train my neural network on that part. So that's why it becomes resolution independent.
Right.
And the black dot shows you if you don't do this PCA step, just train it directly on this data. So 64, and you see the error really blows up as you change resolution. So this architecture that I showed you is what enables you to get resolution independence.
The neural operator you're learning it's mapping the continuous space to the continuous space.
That's right.
That's why. Okay.
So I would expect that it will fall apart if I go close to 421 square, because that's of course the original. That's the only thing I know about the operator. But okay, but away from there, it's quite reasonable. If I just did some kind of linear regression, this would be my error up there. So you do much better than linear regression. Hope so. Okay. The other thing I'd want to show you is something which is quite interesting. So when you do the PCA, the blue line, so let's start with the red line is for 30-dimensional reduced to 30 dimension. If you use 70 dimensions, you do better. The error drops. But then if you use 150 dimensions, the error increases. And the reason is that at that resolution, suddenly the network that you're using and the data you're using did not train the network well enough. So here's what shows you this. So for 100, so this is shows you the training data set, and you can see that if your training data is small, with blue, this is where you get the best resolution, then you go. But then if you increase the size of the training data, you can really reduce the error with using higher dimensions. So what it means is that, yes, you can get better resolution, better learning with a higher dimension, but that also means that the amount of training data you need to train that network is much higher. So that's really a representation of this expectation here. So there's some, you have to be careful that if you have a more complex network, you need more data to train. So, okay, so I showed you some example. I don't know what this is. Sorry about that. I showed you an example with with this elliptic operator. This is the example from DFT work from Ingshi's thesis. So here what we're doing is we're taking a very simple problem. I'm taking a unit cell, I'm deforming it by some f. So this is actually just a finite dimensional map. And I calculate the electronic states. So this is infinite dimensional. And I want to learn the map from f to this electronic states. And we use the same architecture on this side. Here we don't need any PCA because it's already finite dimensional, but here we do. And okay, so that's what we do, the same architecture as before. So this is the ground truth, this is the prediction, this is the error. And here's really what I found very remarkable. So we were trying to calculate energy. So this is the ML. If I learn the energy directly, this is the energy. So this is really a map from a finite dimensional to a finite dimensional. So it's the classical neural net. In this particular example, you can get pretty good errors, which are acceptable. But if I learn the electronic fields and then use that electronic field to calculate the energy, you can see I really can remarkably reduce the amount of error that I have from here to here. So what it is telling you, the fact that you can learn this kind of solution operator gives you very significant error. And in a way, it also shows you not only that you can use ML to learn the solution, but you could, if you really want very high accuracy, you can also use it like a preconditioner. So you can, because the methods you use often are iterative, and so if you have a good initial guess or a preconditioner, that is a very significant thing. And in a way, I interpret this machine learning as a preconditioner because we do one self-consistent loop after that. So the third example I want to go, and I'll spend some time on this and really talk about multiscale modeling, is crystal plasticity. And so what you have is you have a unit cell here, some 3x3 or 2x2 unit cell. You have multiple grains, and in each grain, you have a very large number of slip systems and twin systems. In this case, each grain had something like 48 twin and slip systems, so because this is a low symmetric crystal. So all the grains have the same physics, but their orientation is different. You're given this stress history, and you're trying to predict, the strain history or the deformation gradient history, and you're trying to predict the stress. Right? So the initial microstructure is given. We subject it to some deformation, and we are trying to predict the stress. Very good. So that's what, okay, so this is the strain history. This is the stress history. So the question is, what is the sample, or what is the distribution from which I want to sample my deformation gradient history, right? And this is the sampling we chose. We took this time interval 0 to t, chopped it up into n segments, and then we did a Gaussian process on that and smoothed it so it can go up and down in each of its components. That's what we chose. We tried both having kind of uniform time segments and random time segments, and I'll show you both. That's how we generate the data. And I'm going to show you data for both 2D FFT full resolution calculations and 3D where the data is generated by Taylor averaging. So that's kind of what we did. Okay. Now notice that what I have really is I need the stress, the deformation gradient history up till time t, and I give you the time t. But the architecture I have is for functions from a fixed interval to a fixed interval. So that's what we are, that's what our data is. And we're learning this function. So in some ways, there is no reason why this operator would have to be causal, but the physics is causal, right? So, so that's something we don't assume that our architecture is causal. And one of the tests would be whether we learn causality from the data. Okay. So here's kind of the example. So this is the input. And you can, this is the output. So this is the truth and the approximation. So we do reasonably well, both with fixed and random. And this shows you some summary of how well we do in learning. And let me focus on the 3D. So if both your test data and training data is sampled on a random intervals, then with training with 30,000 paths gives you a PCA error of about 10%, gives you not a PCA error, but it gives you a total error of about 10%. So that actually 10% looks large, but it actually looks something like this. So you get very reasonable solutions from this. Okay. Again, the same thing that we have checked with resolution. So this is what you would get. It's the error is resolution independent. And again, you see with the different PCA dimensions, you get different errors. Now, one point I wanted to make here was that the error really comes from the, okay, so we have errors at the PCA and we have errors at the neural network. And the errors, large errors, are really on the neural network. The PCA error is here. This is the total error. So the dominant source of the error is in the training of the neural network. Here's some kind of common paths which we use in mechanics to test constitutive models. So those are some paths. And here's showing you that even though our architecture is not causal, the data teaches the network, the operator, the causality. So here's multiple paths, all of which up till time TB are the same, and then they diverge. And we find that you see that this is the learned, all these paths remain exactly the same up till that point, and then so despite the fact that we're training on the whole interval, in this region where all the paths were the same, all the responses are the same, showing that it really did learn causality. Here's the other test. I have multiple tests where each of them, the first one goes up till here, then oops, sorry, departs. Then the second path goes up till here and then departs. The third path goes up till there and then departs. And again, you see that it really does learn in the causal parts, in the parts which are common, it actually follows this common trajectory and departs only when the input trajectory departs. So you can do other obvious checks, learning symmetries, learning other things that we know from kind of physics that should be true. And it all of that works very well. We also then went ahead and then they said, okay, let's really try to see whether I can use it in an FE square mapping. What we did was we wrote our neural operator as a user material in Abacus. Why Abacus? Because that's what we want to do. That's what we used. And so basically now we have an ML surrogate, which is serving as our material model. And here's some simulations. So this is the kind of punch with, so you train the VUMAT with, and once you write it, you can change boundary conditions. You can do punches with different plate thickness. You can do the Taylor impact, again, with different size, and you can look at it in many different ways, and it works quite well. So what's the cost? So this is the cost. So let me look at the Taylor anvil. We ran it on a single processor using Abacus. If I use a classical constitutive model like Johnson-Cook, in this particular processor, it took about 50 seconds. If we did our trained VUMAT, it takes about 9 times that. And it's the same thing for the plate impact. And we have tried many ways, many other problems, and it's always factor somewhere between factor 8 to 10, somewhere in there. Okay, you have to pay a one-time offline cost for training the data, and that was 10 to the 6. And the offline training, offline cost of generating the data, which was 10 to the 6, and the offline cost of training, which is 10 to the 4, but on a GPU. So let's take a factor 100 just to kind of. Okay, this is large, but on the other hand, if I really did a concurrent or an FE square calculation, a single calculation would have taken me 10 to the 8. So I'm getting the accuracy of concurrent model, which would have cost me 10 to the 8 at a cost which is comparable to the traditional model. So this really is an effective architecture. And I'll show you another architecture soon, which we're working on at the moment, where this number gets knocked down to something which is very comparable to this. So this becomes an effective tool for doing multiscale modeling. Okay. So that's what I wanted to say. So it's an effective approach. So you can really get accuracies comparable to concurrent multiscale with the cost of traditional constitutive relation. But there are problems with the architecture I showed you. You really have to know the entire history. So you somehow have to know the duration a priori. And so if you want to do a calculation which is longer than that, you can't use this network. So that's one problem. So one question you can ask is, can I learn a Markovian approximation where, given the current state, I can predict the update? And we'll come back to that in a second. In this particular case, I have to train a material model for every virgin material because I'm mapping the strain history to the stress history. So one of our active areas of work is try to understand what about the microstructure, what is we have to keep track of, what aspects of the microstructure do we have to keep track of. Okay, then there is also in the large scale problem, in the fine scale problem, we did not keep track of inertia. So that's, okay, so we'll have to figure that out. And okay, there are other applications which we have, which we're working on. But I want to focus a little bit on this. Can I find a Markovian approximation? Or in some ways, it's also related to the next question here. Can you learn something hidden about the physics that you didn't know about? So we thought about it. And so again, we're trying to learn. What I showed you was learning the entire map. Now the question is, can I learn it from an update? If I give you a strain update, can you calculate the stress update from a model like this? Well, you need something about the state of the microstructure. So you need something about the current state, and it has to give you the new state. So, but I don't want to make an assumption of it. I don't want to make this known a priori. I would like to learn it. So the question is, can I also learn this hidden state variable? So we took some inspiration from mechanics, how we formulate macroscopic models, and we said, okay, let's try the following architecture. I'm going to say that the stress at time t will depend on the deformation gradient at time t, some rate of change of deformation gradient at time t, some hidden variable xi, and the hidden variable evolves according to some first order dynamics. So it's some kind of overdamped dynamics for the hidden variable. It's a very common structure that we use in mechanics and material science. So Landau-Ginzburg models, all of these we use. So can we see whether that architecture works? Of course, the point is we don't know the function f and g, and we don't know the hidden variable zeta, right? So what we'd like to learn is use our training data set to learn these functions f and g, theta, and this hidden variable zeta, this hidden variable zeta. So that's what we'd like to do. And when we started testing it on some simple 1D viscoelastic models, so it's 1D, so the stress depends on the elastic modulus, which might be spatially dependent, and some viscosity, which again might be spatially dependent. So in this case, we can prove an approximation theorem with this particular architecture, where we use essentially some of the features of this model. But this is what we learn. So if I don't use any hidden variable, then I get a large error. If I use one hidden variable, I get a smaller error. And more or less the data in this particular example, you learn from using about 3 hidden variables. So it begins to learn the data with 3 hidden variables. The architecture I used here was strain rate dependent, but suppose I don't have this, it turns out that it becomes the error becomes resolution dependent, whereas if I use the strain rate in my architecture, it becomes resolution independent. And we know from the approximation theorem that that has to be the case. So this is kind of the numerical test. We also did this on 1D viscoplasticity, a very simple model. And so here, there's no averaging. So we know that there is only one state variable. And the question is, can you find it? And we can show that the best approximation is with one hidden variable. And in fact, the hidden variable up till some inessential constant tracks the plastic strain, which is the hidden variable in the model that I start. So I want to emphasize that what we're providing it is epsilon as a function of t and sigma as a function of t, and it is learning epsilon p from that data. And we have now extended it to 3D polycrystals and are implementing it, and we're trying to understand the errors. And in fact, our preliminary tests, as I mentioned earlier, are really very encouraging, where we are able to learn a lot about the macroscopic plasticity. So we are following a similar approach in trying to learn the texture problem, so to try to learn the dependence on the microstructure. And so hopefully in about a year or a couple of years, we'll have some, be able to update you. So in the last 5 minutes or so, if I may, or I'm happy to stop here, or wanted to make a couple of comments about
Please go ahead. Yeah.
Thank you. About a more general, how this fits into a more general, I showed you a couple of particular architectures, but I wanted to make you comments about the more general about neural operators. So this is the kind of maps that we are interested in from some function space to another. And so as a general architecture, this is what we have been studying. So if you recall in the PCA-NET, I had a projection here and a lifting here, and then I had a neural net in the middle. So more generally, what we want to do is the following. So we still have some kind of linear operator, but it's local. So in other words, if I give you some function, B at any point X only acts at that point X. So it's a very local operator. The middle layer is you have some activation function, your favorite one. Then you have a local operator L, some bias W. So that is exactly what I showed you. But then we add a non-local integral operator here, right? So at any given point, KV returns a value which samples not only X, but all its entire neighborhood. And the other one you could do is rather KV would be the inverse Fourier transform of a linear transform of the Fourier transform of V, right? So it would be something like that. Okay. And for this, we can go ahead and prove an approximation theorem. It says that if F and S are Banach spaces and phi is continuous on these Banach spaces and maps between Banach spaces, we need some technical hypothesis which I've omitted. Then you can prove an approximation theorem that we do indeed have a neural network and a training which provides you with an error. And here it is the soup error over some compact set. Okay. So this holds for the previous PCN net as well. And so this is actually, so it extends the previous theorem, but it extends to all theorems, all kind of architectures of this class, which, okay. So I thought I'll show you one example of this. It's the so-called, what we call the graph kernel network, where, okay, so we have an integral operator. And okay, I don't know how to, my data is already, might be discrete, so, and I don't want to evaluate this whole integral. So we do some Nystrom approximation at some points. And then I can also incorporate multigrid structure to it. So basically the value at this point comes, so in other words, the value at this point comes from some neighboring points here, comes from some other neighboring points here. You can use multiple resolution, and this gives you a very strong architecture. It turns out that you can show that more, if, okay, so you can show that this requires much less data to train. You can get super resolution, but it turns out that the evaluation of networks like this is much more expensive. So in the case of multi-scale modeling, where I want to use this in a larger scale model and I have to use it, evaluate it repeatedly, it becomes completely prohibitive. But in areas where I'm trying to learn from sparse data, where I might have some data from a smaller resolution and I'm trying to understand the solution operator, this becomes an extremely powerful method. And that's something as a way of doing multi-resolution calculation. And that's something that we have been kind of trying to explore. I had some other comments I wanted to make, but I'll skip over that. And I'll stop here with a list of much of this work, actually all of this work is certainly available in preprint. Some of it is published, but much of it is available in preprint form of the archives. So I'll leave this slide up, and I'm happy to answer any questions or receive any comments and suggestions.
Thank
very
you.
much.
Thank you. Thank you so much for the wonderful talk, Kaushik. I loved it a lot. We do have a question from Saurav. He asked, can an operator that maps multiple input functions to multiple output functions be learned this way? He means PCA-NAT. And would there need to be any assumption on the spaces that the input and output functions need to lie in?
Okay. So the answer to the first part of the question is yes. So, you know, if I have multiple input functions and multiple output functions, I'll think of that as a higher dimensional input function and a higher dimensional output function. If I can think it that way, this architecture works. There's no limitation on the dimension of the input function. So in fact, when I talked about the strain space to stress space, I'm mapping from a 9-dimensional space to a 9-dimensional space. So, okay. And in the case of the DFT calculation, for example, my output was multiple things, multiple components of the electronic structure, and you can use this. Now, as I mentioned, you're learning, so you really need to know somehow the distribution from which your data is coming from, right? And you need to know that you're sampling a meaningful sample, that your sample size is test size is sufficient. And while we have these universal approximation theorems, they tell you about existence, right? It tells you that there exists something. It doesn't tell you how to find it or when it is sufficient, right? And that's one of the kind of big open questions in the field, and everything we do suffers from that as well.
All right, sounds good. Okay, another question from Kim Kai. Can you also comment on the Fourier neural operators and also the neural operators on nonlinear PDEs?
Yeah, so on the Fourier neural operators and the graph kernel operators, we have tested this on, a linear PDE, but the map is nonlinear, right? It's from the coefficient to the solution. So that's the one I showed you. In fact, actually, maybe I think I have a backup slide from our recent paper there. Yeah, so I had this. So this was the solution from the error in the solution from the A of X to U. So that's the PDE is linear, but the mapping I'm trying to learn is nonlinear. And okay, so this is resolution, various resolutions, and these are the errors for a given data set. So, and this was a very small data set, and the Fourier neural operator and the graph neural operator really does very well, because you're really learning, in essence, the Green's function of the solution operator. So with very small amounts of data, you can really learn it. It provides super resolution, as I showed. But you have to take a Fourier transform, so that's expensive, or you have to evaluate you have to do an integral operator, so it's expensive. So in the context of multi-scale modeling, it's not the greatest thing, but if you're really trying to learn the PDE, we have also done this for learning the Burger's equation and Navier-Stokes. And once again, the Fourier neural operator does very well in those PDEs. And the graph kernel does not as well, but very good as well. So these numbers are representative of not only this example, but the Burger's equation and Navier-Stokes with limited Reynolds number. I actually forget off the top of my head what the maximum Reynolds numbers we went to.
Okay, thank you so much. My question is, can you go back to the slide 20?
Okay, slide 20. There you go. Yeah.
Oh yeah, here. So you compare the computational cost, the various computational costs. That is nice. And I have two questions on this slide. The first one is the offline data, generations and offline training. It's a multi-scale, so you train the neural net on the micro scale, which is the the small compared to the macro scale system level.
That's right.
So I was expecting somewhat efficient training procedure because the data size you're dealing with is smaller, but maybe you need a lot of data, I guess.
So yes, okay, very good question. So what we needed in this case with this PCA-net architecture was of the order of 10,000, I don't remember exactly the number, 10,000 trajectories. So I had to do 10,000 calculations. And this is the estimated cost on a single CPU, right? I mean, so I wanted to keep everything. So I said, okay, if I had done each of these calculations on a single CPU, what would it cost? And that was this 10 to the 6 to generate the data.
Add them up. Okay.
Now,
Okay.
Of course, I can do this trivially parallelly because it's
Oh,
independent
yeah.
realizations.
Right, right.
And with the kind of recurrent neural operators, we find much better accuracy with just 400 trajectories because it's learning much more the structure of the problem. Here it is not learning the structure of the problem. So in this particular case, this number is large, but I think uh, this is something we can knock down with a better architecture and also doing better data science of trying to sampling in a better way.
Okay. I guess it can be improved.
Absolutely. And for the problem with the RNO net, some of the tests we're doing, you knock it down by a factor it's about of the order of 1,000, if I remember correctly. So it knocks down by 10 to the 3.
Okay, sounds good. And
So yeah.
my second question on this slide is, okay, so you nicely have the comparison between the concurrent multiscale and your data-driven, the multiscale, the results on the computational course. How about the accuracy?
So
How different are they?
okay, good question. We never did the concurrent multiscale, right? This is the estimated based on the number of elements and the number of
Ah,
realizations I would have to do.
I see.
But I expect accuracy to be good because what I've done is I have done a lot of testing of the model itself, right? So the model itself is very accurate. And so basically, it's basically replacing one material model with another. And if the material models are the same, the integration schemes are the same, I would expect the same accuracy. So while in this context, I have not done the full comparison, I would expect even in this, that would be the case. We have done the full comparison in simpler 1D problems, and it bears it out. Okay. Being at a university, I don't always have the computational resources that you guys have. So
Yeah. Well,
the
then we
concurrent
can,
multiscale is not something I could
yeah, simulate,
venture.
right? Yeah, well, for that, and we can collaborate,
Of course,
right?
I would be delighted to do that. Yeah,
We do have machines, and you do have the algorithms, so we
of
can.
course. No, yeah, no, I'd love to do that. Yeah.
All right, sounds good. All right, thank you so much. Is there any other questions from audiences? You can unmute yourself and ask directly if you do have one. Otherwise, let's thank our speaker for the wonderful talk, and I loved it. I learned a lot, and I especially like the preconditioner, the
Yeah.
perspective. So very, very well done. Thank you
Thank
so
you
much
so
for the
much,
great talk.
Youngster. It's a
Yeah.
pleasure. And if you don't mind, at some point, you mind sending me the link of the talk?
Yeah, yeah, I will definitely do so. Yeah.
All right, great. Thank you. Bye.
Thank you. Thank you.